Welcome to this narrated presentation sharing my internship experience at Walter and Eliza Hall Institute of Medical Research. My name is Jia He, and I'm doing second year Master of Data Science at the University of Melbourne. Today, I'll be sharing my internship experience at the Cryo-EM Data Science Research Group at WEHI. In today's presentation, I'll first introduce my internship institute, WEHI. In the main section, I'll be talking about what I did during the past few weeks and how does our work fit in the wider world, emphasizing on the significance of our project, ending with conclusion and acknowledgement to express my gratitude. The idea for Australia's oldest medical research institute was formed in the late 19th century. It came to life in 1915, founded by Walter and Eliza Hall. Since then, community-driven philanthropy has been at the heart of WEHI's success. Today, it is now a community of researchers, students, and professional service staff who work towards achieving discoveries that improve human health. With more than 1,300 staff and students and more than 90 laboratories, WEHI's research area expanded to cancer, lifelong health, infection, and immunity. Our internship department is called the Research Computing Platform, which is based in a computational biology theme, aiming to support and advocate for WEHI's computational research. But what exactly can a university data science student do at a medical research center, and how would this benefit the society? In order to answer this question, the core focus of today's presentation is to explore how our work integrates into the broader global context. Let's begin with some domain concepts. Cryo-EM stands for cryogenic electron microscopy, which is a cryogenic microscopy method used to visualize the 3D structure of biological molecules. Different from traditional microscope techniques, which usually involves the process of crystallization, this technique stands out by preserving sample in near native state through flash freezing in vitreous ice. This would minimize radiation damage and give space to study the molecules that are difficult to crystallize. This technique is important because it is crucial for understanding the molecule's function and aiding drug development and advanced medical research. Although cryo-EM is a very promising technique, there are some challenges, and a big one is selecting high-quality images for further analysis, as a large number of images will be produced and only a part of them can be used. This is why we need to apply machine learning into Cryo-EM to facilitate this process. To understand this challenge and potential solution better, let's introduce the Cryo-EM workflow. The general workflow in Cryo-EM includes preparing the sample where we would freeze them into vitreous ice, and after this, in the electron microscope stage, a set of 2D projection images will be produced. This process is done through an electric gun, which will emit electrons that passes through the sample from various angles, creating a series of 2D projection images. However, not all of those images are of good quality. As we can see from this image, it is difficult to distinguish the background from the particles. This is because we have to emit electrons at a relatively low speed so that it doesn't destruct the protein structure. So this is where machine learning algorithm plays a critical role, as they will be employed to examine a series of 2D projection images and select the ones that are suitable for further analysis. So using the quality images, a 3D classification and reconstruction process is undertaken. This process combines the 2D images to form a detailed 3D dimensional representation of the protein structure through mathematical calculations. This offers valuable insights into its characteristics and functions. Let's delve deeper into the particle picking stage, where our work is mainly focused on. So particle picking in Cryo-EM is the process of identifying and selecting individual particles from images for further analysis. The focus of our research project is to develop an algorithm that actually facilitates the particle picking process by filtering the good holes to do particle picking. Let's explain how this works. Before the particle picking process, the electron microscope will take images of the cryo-EM grid, square, and holes. Each cryo-EM grid comprises multiple squares, and within each square there are several holes. The particle picking process happens at the hole level. However, not all of the holes are of good quality, as we just mentioned. If we can't decide which holes are good to inspect at the square level, we may waste some time inspecting the bad holes. So, what if it looks like this? Where we know which holes are good and which holes are bad. So we only need to look at the holes of good quality. Therefore, we hope to develop a machine learning algorithm that can cluster the whole images into two groups, the good and bad groups, so that we only need to inspect the good groups. It is more time saving and money saving, as it costs more than $200 per hour to use the cryogenic microscopy. So to summarize our solution, we aim to develop an unsupervised machine learning algorithm to cluster holes into good and bad cluster. This will be done firstly by identifying and extracting the usable holes from a square image, where the cut out ones and the edge located ones will be eliminated. As suggested by this image, only those holes will be used. Then we will apply K-means algorithm to cluster the whole images into two classes as suggested in this image. The purple dots represent cluster 1 and the yellow dots represent cluster 2. However, we can't decide which cluster is good or bad based on the nature of K-means algorithm. Hence, we need to invite experts to take a look at the samples in each cluster to decide which cluster is good or bad. Our methods still have space for future development. We suggest researchers to explore supervised machine learning algorithm where experts can be invited to label a set of good and bad holes as templates for the machine learning algorithm to study. However, this research topic did not come across straight. In fact, as a research intern student, besides developing and applying the technical approaches, we spend most of our time understanding the domain concepts. We are not given with this research question at first. Instead, our supervisor gave us flexibility and space to learn and explore the topics by ourselves, giving us a sense of how research work is like in real life, where at most time we don't know what the question is good to study at first. And those are work as appendix of what I did each week. In conclusion, Cryo-EM bolstered by machine learning is a powerful tool that is reshaping our understanding of the biological world. Our work fits in the wider world at 3 levels. In the particle picking level, our algorithm facilitated the particle picking process with machine learning automation, and we set up a study framework and provided insights for future studies. At the internship program level, we pipelined the Cryo-EM research framework for future interns so that they can study the topic in a more efficient and structured way. And both of those benefits would contribute to the Cryo-EM research level, where structural biologists would understand the molecule structures in a more efficient way in order to assist drug development and medical research. Last but not least, I want to present my sincere gratitude to my supportive supervisor, Roland, and my teammates, Marlon and Mary. Also, I want to thank the science internship team for arranging this course. It's an exciting time in structural biology with these technologies leading us towards a groundbreaking discoveries and innovations in medicine and beyond. Thank you, and those are the references.